Hello students, I'm Dr. Sheetal Ghorpade from RMD Silver School of Engineering. Today I'll be conducting lecture on curve tracing, topic from Engineering Mathematics 2 subject. So it is unit 4 of your syllabus. Contents of this unit are Cartesian curves, parametric curves, polar curves and rectification of curves. Cartesian curves means equation of curve is given in terms of x and y. In parametric curves, x and y are expressed either in terms of t or in terms of theta, that is in single variable. And polar curves are in terms of theta. Rectification means finding the arc length. Total weightage of this unit is 17 marks for end semester examination. Students, all of you have studied various types of curves since your school education. Rectangles, there are all types: circle, ellipse, hyperbola and parabola. All these are standard curves. You know the formula for finding their area, perimeter, then arc length and so on. But in real-time applications, it will never always be possible that all the shapes are in the standard form. When you go for designing of certain product, the shape may be random and you need to find area of that shape, arc length for that shape. And for such random shapes, you need the knowledge of curve tracing. So we'll be studying here curve tracing to know the shapes other than the standard shapes. In addition to that, area of such shapes will be determined by using multiple integrals that we'll study in the coming lectures. Most important thing that everyone must know before starting the curve tracing is the difference between multiple point and the double point. So here in this figure 1, out of this origin, 3 curves are going. Of those 3 curves, 6 branches are there moving out of this origin. Means multiple branches are going outside of this point and hence we call it as multiple point. Whereas in figure 2 of this origin, only one curve is going outside and which has 2 branches. So exactly 2 branches are going outside. So we call it as double point. Double point has lot of importance in curve tracing. Depending on nature of the curve at nature of the tangent at double point, it is divided in 2 types. First is node. See here at the origin, it has 2 branches, means it is double point. When we find tangent at this double point, the first tangent is the line y equal to x and the another tangent is the line y equal to minus x. Means this one point has 2 tangents which are real and different. So such double point is called as node. That is the double point having 2 distinct real tangents is nothing but the node. Whereas this is also double point. It has only one tangent. Such double point which is having only one tangent is called as cusp. This tangent is the vertical, so we call it as vertical cusp, and this tangent is the horizontal line, so we call it as horizontal cusp. So node and cusp are very important while tracing the curve because they decide the convex or concave nature of the curve. Now, after studying the concepts of node and cusp, we'll move to the first type of curves, that is Cartesian curves. Cartesian curves are again divided into 2 types. The first one is explicit relation and the second is implicit relation. In explicit, y can be directly expressed in terms of x and x can be expressed in terms of y. So we'll see now the rules for tracing explicit curves. First point, symmetry. To check symmetry about the coordinate axis, we have various conditions. First thing, all the powers of y are even in the equation of curve, then it indicates that the curve is symmetric about x-axis. Whereas, if all the powers of x are even in the equation of curve, then it is symmetric about y-axis. And if both x and y have even powers, then it is symmetric about both the axes. So in short, how to remember? Even powers of y indicate symmetry about x-axis. Even powers of x, symmetry about y-axis. Both even, both axes. Then the next case is symmetry about the line that is in opposite quadrants. That is about the line y equal to x and y equal to minus x. The first case, if we replace x by y and y by x in the equation of curve, it remains unchanged, then the curve is symmetric about the line y equal to x. For example, if you take the equation of curve xy equal to c, interchange x and y, equation remains same. So it is symmetric about the line y equal to x. Similarly, for the line y equal to minus x, we have to replace x by minus y and y by minus x. If the equation remains unchanged, then it is symmetric about the line y equal to minus x. Most of our curves fall in the first three categories, and the explicit curve falls in the category 4, that is symmetry about the line y equal to x or y equal to minus x. After symmetry, the next point is to find points of intersection. First case, whether the curve passes through origin or not. You can check it in two ways. Substitute x equal to 0, y equal to 0. If it satisfies the equation of curve, then it passes through origin. Or at first sight, by observing the equation also, you can identify it. If your equation does not have any constant term. Constant term means either the constant real value or the constants like a, b, c and so on. If the curve passes through origin, then it will have tangent at the origin. To determine tangent at origin, we have to equate lowest degree term of the equation to 0. Remember, lowest degree term of the equation to 0. That is, if the degrees of the terms in the equation are 3, 2, 1, then all the terms having degree 1 will be equated to 0, and that will give us the equation of tangent at the origin. After finding nature at origin, we have to find points of intersection on the coordinate axis. To find point of intersections on coordinate axis, we substitute y equal to 0, will get the x-intercept, x equal to 0 will get y-intercept. So once you determine these points, then naturally we have to find tangents at these points. To find tangents, first find the value of dy by dx of the given equation. Then substitute the value, that is substitute the point in dy by dx. If the value of dy by dx is 0, then the tangent at that point will be parallel to x-axis. And if the value is infinity, then the tangent will be parallel to y-axis. So in short, when you remember that if your curve is symmetric to x-axis, your tangent at point of intersection will be parallel to y-axis. Whereas if it is symmetric to y-axis, tangent at point of intersection will be parallel to x-axis. After this, the most important concept comes, that is asymptote, which is totally new for you. So all of you know the concept tangent, but some curves are infinite curves, they are extended till the infinity. So tangent drawn to that curve at infinity is called as an asymptote. So asymptote is tangent at infinity. To find tangent at infinity, we have two ways. First way, if your curve is symmetric to x-axis, equate coefficient of highest power of y to 0, opposite variables. If it is symmetric to y-axis, equate coefficient of highest power of x to 0. See the difference. Here we are equating coefficient to 0, and while finding tangent at origin, we are equating lowest degree term to 0. Their term equal to 0, and here coefficient is equal to 0. And hence both the cases will get combined if your curve is symmetric to both the axes. So for both symmetry, both the axis symmetry, you equate coefficient of highest power of x to 0 and coefficient of highest power of x to 0. Or find the values of x for which y becomes infinity. All those values will indicate asymptote of that curve. Find the value of y for which x becomes infinity. So those values of y are the asymptotes. So this way we have to determine asymptote. Every curve will have asymptote is not true. Some of the curves may have asymptote, some may not have asymptote. So as we go on solving the problem, this concept will become more clear to you. Now, to trace the curve, we must have to determine in which parts of the plane my curve exists. That is, we have to get the partitions, that between which lines, between which quadrants it is existing. And for that, if your curve is y equal to f of x, then identify the values of x for which your y is imaginary, means y square is negative. And if the equation of curve is x equal to f of y, find the values of y for which x is imaginary, that is x square is negative. So for all those values or for that range, your curve will not exist. In that range, your curve will remain absent. Hence, you divide the range minus infinity to infinity in such a way that you have to identify existence and non-existence of the curve by using the table. So these all are the rules for tracing Cartesian curve. We'll summarize it first. The first point is symmetry. Powers of x even, symmetric to y-axis. Powers of y even, symmetric to x-axis. Both even, both the axis. If it contains constant term or 0, 0 satisfies equation, then the curve passes through origin. If it passes through origin, it will have tangent at origin, and to find that tangent at origin, equate lowest degree term of the equation to 0. Once you get the idea about origin, move forward and determine intercepts with coordinate axis. To find intercepts with coordinate axis, substitute y equal to 0, get the values of x, x equal to 0, get the values of y, and hence you will get points of intersection with x-axis and y-axis. After finding points of intersection, identify the nature of tangent. For that, you need to determine dy by dx. Find the value of dy by dx at each point of intersection. If it is 0, tangent is parallel to x-axis. If infinity, tangent is parallel to y-axis. In short, when the curve is symmetric to x-axis, tangent will be parallel to y-axis and vice versa. After that, we have to determine the asymptote. For asymptote, find the values of y for which x is infinity, or find the values of x for which y is infinity. And then to find the region of absence, identify the values of x for which y square is negative, means y is imaginary, and values of y for which x square is negative, means x is imaginary. So I think now all the rules are clear to you. Each rule has certain subcases, but when we draw with the curves, we will have only one case under each point, and the concept will be more clear to you. So we'll be seeing examples in such way that every case will be covered in our problems. Now we'll see the first problem. Trace the curve y square into x minus a is equal to a square into 2a minus x. Here a is constant. Power of y is what? 2, which is even, whereas power of x is 1, which is odd. Hence, the conclusion is it is symmetric about x-axis. If you simplify the equation, y square minus a y square is equal to 2a cube minus xa square. So what is constant term over here? 2a cube. 2a cube is constant. Constant term is there. What it indicates? It will not pass through origin. Hence, we have to find points of intersection now. Since it is symmetric about x-axis, I'll choose to substitute y equal to 0. When I'll substitute y equal to 0, I'll have a square into 2a minus x equal to 0, and hence x equal to 2a. So the point of intersection with x-axis is 2a 0. And in this case, your tangent will be naturally parallel to y-axis. So we can write directly dy by dx at 2a0 is equal to infinity. So first three cases are covered. Now what we need to check? Asymptote. For finding the asymptote, it is symmetric about x-axis. Equate coefficient of highest power of y to 0. What is highest power of y? Y square. Its coefficient is x minus a. X minus a is equal to 0 indicates x equal to a, and hence an asymptote to this curve is x equal to a. Other way, if you write it as y square equal to a square into 2a minus x divided by x minus a, for which value of x y square is infinity? For x equal to a. Hence, x equal to a is an asymptote. Once we determine with an asymptote, we need to find region of absence. Now, I'll give you one hint. Your curve has only one point of intersection. What is that? 2a 0. And what is asymptote? X equal to a. So it gives us the range that how to divide the plane. Before a, I will consider one part of the plane. Between a to 2a, one part, and 2a to infinity will be other part. So this is the line x equal to a. So this point is a0. So before this is the one region. This is the another region, and this is the third region. Now, before a, substitute say x equal to a by 2. If I write x equal to a by 2, your y square will be negative. Hence, y will be imaginary. Take any other point, say a by 4, then also your y square will be negative. Same way, after 2a, take the point, say 3a, y square will be negative. Hence, your curve will exist only between a to 2a. So all the points are clear. The curve will not pass through origin. So here we don't have curve. It has an asymptote x equal to a. Tangent is x equal to 2a, which is parallel at 2a0. And now we have to identify the nature. Since this is an asymptote, so this curve will be extended till infinity, and here it must touch to this line. So we should take the nature of the curve like this. We should not take like this, because if we draw like this, what it means, the tangent is x-axis. Our tangent is not x-axis. Our tangent is what? The line x equal to 2a, and hence this is the double point which has only one tangent. So I can call it as cusp of this curve. So this way, if the question comes in exam, you have to write these 5 points, and the rough nature of the curve must be drawn. So this is first example in which curve is not passing through origin. Now we'll see the next. So this is the curve. Y square equal to x minus 1, x minus 2, x minus 3. It is the cubic curve. So again, when we'll take the product, the constant term will be minus 6. Power of y is 2, which is even. Hence, it is symmetric about x-axis. Since the constant term is there, it will not pass through origin. Now we have to find points of intersection with coordinate axis. Since symmetric to x-axis, put y equal to 0. When I'll substitute y equal to 0, I'll get x equal to 1, x equal to 2, x equal to 3. Hence, my intercepts with x-axis are 1, 0, 2, 0, 3, 0. So, there are 3 points of intersection on the axis of symmetry. Now, dy by dx at each point will be infinity, because the tangents will be parallel to y-axis passing through these points. Now, asymptote. Curve is symmetric to x-axis. At the first sight, you can see there does not exist any value of x for which y is becoming infinity. Or the coefficient of y square is 1. Hence, there is no asymptote. In the previous problem, we have seen there was an asymptote x equal to a. But here, asymptote does not exist, because there does not exist any value of x for which y is infinity. So, your curve will not have an asymptote. Now the region of absence. So in this case, what I'll do, I'll divide again the plane minus infinity to 1, 1 to 2, 2 to 3, and 3 to infinity. For minus infinity to 1, if you put 0, your y square is what? Minus 6, which is negative. Hence, before 1, your curve will not exist. Put x equal to 1 by 2. It will be minus half, minus 3 by 2, and minus 5 by 2. Again, the product will be negative. So, the curve does not exist before 1. Now, we'll check between 1 to 2. Substitute 1.5. I'll get here 0.5, minus 0.5, and minus 1.5. These two terms will be negative, and this one will be positive. So the product will be positive, and hence y square is positive, means the curve exists in this region. Now between 2 to 3, take any point, say 2.5. If I put 2.5, I'll get here positive, positive, but this will be negative. So the product will be negative, and hence the curve does not exist between the region 2 to 3. Now we'll substitute 3.5. For 3.5, all the terms are positive, and hence the curve exists after 3 till infinity. So in which region your curve is existing? Between 1 to 2 and between 3 to infinity. One thing which you have to remember now is whenever there are 2 points of intersection and the curve exists in that region, then always that is loop. So directly you can draw a loop between these 2 points, 1, 0 and 2, 0. And after 3, the value of y will go on increasing. We can observe it from equation. So the nature of curve is like this. So we have drawn the tangents at 1, 0, 2, 0, 3, 0, which are parallel tangents. There is loop between 1 and 2, and curve is infinitely increasing after 3. So this is the case where asymptote does not exist. What the difference between previous example and this example? In the previous one, there was asymptote. Here we don't have any asymptote. Now the next case. Here, equation of curve is y square into x square minus 1 equal to x. Again, the power of y is even. So, symmetric to x-axis. X square y square minus y square is equal to x. Are you getting any constant term here? No. So, the curve will pass through origin. Last 2 curves were not passing through origin. It passes through origin. Since it is passing through origin, it will have tangent at origin. X square y square degree 4 minus y square degree 2 x degree 1. 4, 2, 1. What is the lowest degree? 1. So equate x to 0 means what is tangent at origin? Y-axis is tangent at origin. Now we have to find points of intersection. To find points of intersection, now if we substitute, if you check here, it does not have any x-intercept or y-intercept. Hence, there are no other points on x-axis where the curve intersects. Asymptote. Y square is equal to x upon x square minus 1. Put x equal to 1. Y square is infinity. X equal to minus 1. Y square is also infinity. Hence, asymptotes are minus 1 to 1. So we got here 2 asymptotes as well as passing through origin. Now which points are there in our hand? Minus 1, 0, 0, 0, 1, 0. Hence, I will divide my plane in 4 different parts. Before minus 1, between minus 1 to 0, then 0 to 1, and 1 to infinity. We have to check now what happens for each region. Now, before minus 1, put minus 2. What will get here? Minus 2 divided by 3. Value of y square is negative. Hence, the curve will not exist before minus 1. Between minus 1 to 0, substitute any point, say minus 1 by 2. What will have? 1 by 4 minus 1, that is minus 3 by 4. And this is minus 1 by 2. Ratio will be positive. Hence, the curve exists between this region. Now, between the next, that is 0 to 1. Take plus 1 by 2. 1 by 4 minus 1 is minus 3 by 4. So 1 by 2 by minus 3 by 4 will be negative. And hence the curve does not exist in this region. Now the next, greater than 1, put 2. Definitely it will be positive. So among these 4 parts, curve is existing between minus 1 to 0 and 1 to infinity. Now first we'll think of the first region, that is minus 1 to 0. What is first asymptote? X equal to minus 1. X equal to minus 1 is an asymptote and the tangent is y-axis. Means you have to draw the curve like this and it will touch to the line x equal to -1 at infinity. So the part between -1 to 0 is over. Now see here, since there is no point of intersection with x-axis other than origin, so your curve will be hanging over here. It will reach to 1 at infinity. And since it is symmetric about x-axis, same curve will exist here. So this way the whole curve is divided in 4 different parts in upper quadrant and the lower quadrant. Clear the concept? So in each problem, we are trying to cover various cases so that all the concepts of the rules of tracing will become more clear. Next, the curve is y square into 4 plus x square is equal to 4x square. 4y square plus x square y square equal to 4x square. All the terms are even. Since all the powers are even, so what will have? It will be symmetric about both the axes. Now it does not have any constant term. 4y square, x square, y square, 4x square. Hence, the curve will pass through origin. To find tangent at origin, lowest degree term to 0, 4y square degree is 2. X square y square degree is 4. 4x square degree is 2. There are 2 terms which are having degree 2. So equate them to 0. That is 4x square minus 4y square is equal to 0. Hence y square equal to x square means what? Y is equal to plus or minus x. These are the tangents at origin. Definitely, if you check again by substituting y equal to 0 or x equal to 0, you will get only the point of intersection as origin. Hence, there are no intercepts other than origin. Now, asymptote y square is equal to 4x square upon 4 plus x square. Put x equal to -2. What will get? It should be, it is negative sign, so it will be infinity in both the cases. Then the region of absence, we have to find y equal to 2 and y equal to -2 are the asymptotes, means divide the region in 4 or 5 different parts very easily. Before -2, -2 to 0, then 0 to 2 and 2 to infinity. Definitely it will not exist above 2, above -2 and below -2 and above 2. Now the nature of curve, since this is the tangent at origin and this is an asymptote, your curve will move like this and will touch to this line at infinity. Why we have not drawn the curve like this? Because if we draw like this, it will cut the line y equal to 2 at finite point. It should touch to the line y equal to 2 at infinity, and hence the curve will exist only in this region. So this way, since it is symmetric along both the axes, so in the 4 quadrants we have drawn the curve like this. So this is an example where the curve is symmetric about both the axes. Now the next question, trace the curve y into x square minus 1 is equal to x square plus 1. This is little bit different nature of the curve, where the curve is existing at very different places in the plane. If you see, the powers of x are even, so it is symmetric about y-axis. It has constant term 1, hence it will not pass through origin. Naturally, there will not be tangent at origin. Now to find the point of intersection, if you substitute x equal to 0, what will get? Minus y is equal to 1, that is y is equal to minus 1. So what is point of intersection? 0 minus 1 is the point of intersection. Find the value of dy by dx. Naturally, the tangent will be parallel to x-axis, so it should be what? 0. After that, asymptote. Find the value of x for which your y is becoming infinity. X is 1, y is infinity. X is minus 1, y is infinity. As well as y equal to 1, if we substitute x square plus 1 is equal to x square equal to minus 1, which is absurd. Hence, y equal to 1 will also be an asymptote of this curve. So it has 3 asymptotes: x equal to 1, x equal to minus 1, and y equal to 1. Now, so many points we got, so we have to divide the plane very nicely into the distinct parts. First is the line. This is your x-axis, y-axis. This is the line x equal to 1, x equal to 1, x equal to minus 1. Then the asymptote is y is equal to 1 we have drawn. So this way we have the region divided in so many parts. The first thing, between minus 1 to 1, we will have the curve like this, because it should reach to these lines at infinity. Then here, between these points, that is minus infinity to minus 1, again the tangent to the curve is like this. So the curve will be hanging, and hence we will have symmetry. So the same curve will exist over here. So this way, in this curve, we have the scattered arcs of the curve in the whole plane. So I think we have seen curve passing through origin, not passing through origin, having an asymptote, not having an asymptote, then multiple asymptotes, and so on. Now the next is implicit curve, that is in which we cannot express x completely in terms of y or y completely in terms of x. In case of implicit curves, we will not have straight asymptotes, we'll have oblique asymptotes. So method for finding those oblique asymptotes is little bit different. We have to substitute y equal to mx plus c in the equation of the curve. Once we substitute y equal to mx plus c in the equation of the curve, simplify it, then equate to 0 the coefficients of two successive highest powers of x to 0, and then get the values of m and c. So in case of implicit curves, only oblique asymptote exists. Now this is very important question of implicit curve, asked many times in exam, that is x cube plus y cube is equal to 3axy. This is implicit curve. Now if you replace x by y, you will not get the change in equation. Hence it is symmetric about the line y equal to x. So it is defined between the region minus infinity to infinity along x-axis. So it will not have any point which is lying in the third quadrant y, both x and y are negative, indicates x cube plus y cube is less than 0 and xy greater than 0. So you have negative equal to positive, and hence there does not exist curve in the third quadrant. Now substitute x equal to 0, you'll get y equal to 0. Hence your curve passes through origin. Since it passes through origin, it will have tangent at origin. To find the point of intersection with a line of symmetry, substitute y equal to x. If you put y equal to x, you will have 2x cube is equal to 3ax square. Simplify it, you'll get x equal to 0 and x equal to 3a by 2. So what are the points of intersection on axis of symmetry? 0, 0 and 3a by 2, 3a by 2. To find tangent at origin, lowest degree term of the equation to 0. X cube plus y cube is equal to 3axy, 3, 3, 2. What is the lowest degree? 2. So xy equal to 0. It implies x equal to 0, y equal to 0. Hence, both x and y axis are tangents at the origin. It indicates that origin is node since it has two different tangents. Now, it will have oblique asymptote. To find that oblique asymptote, substitute y is equal to mx plus c in the equation of curve. We are substituted over here, then simplify it. The coefficient of x cube will be 1 plus m cube and the coefficient of x square will be 3m square c minus 3am. Equate them to 0. It gives us m equal to minus 1 and c equal to minus a. So y is equal to minus x minus a. Hence our oblique asymptote is x plus y plus a equal to 0. Now to draw that curve, 0, 0 is the point of intersection. 3a by 2, 3a by 2 is the point of intersection. It is symmetric about the line, y equal to x. Tangents at origin are these two. Since the curve exists between these 2 points, there will be loop and it will touch to this asymptote at infinity. So this will be the nature of this curve, and hence this way this implicit curve has been drawn. So we have studied Cartesian curves today, in which you have to remember 5 points: symmetry, origin, tangent at origin, special points, that is points of intersection, asymptote, and region of absence. So for practicing at home, I have given you here 5 problems. If you look at this point, this is symmetric about x-axis. This is symmetric about x-axis, symmetric about both the axes. This is symmetric about x-axis and this is symmetric about y-axis. So likewise, you write all the points and then solve the questions. I hope you all have understood that how to draw the Cartesian curves. In the next class, we'll see how to draw parametric curves. Thank you.